Hi guys, today we're going to be covering integration techniques, basically how to integrate just about anything I can think of. Definite, indefinite, all sorts of ways to do it. So first, let's talk about what you should know beforehand. You should know the antiderivatives of basic functions. So this is like the most complicated function I'll expect you to know the integral of. And what is a u-substitution and how does it work? So basic things from Calc AB if you're taking the American AP curriculum. I'm going to try and speed through this video. Don't want it to be too long, so let's get started. So the first technique I'm going to cover is u-sub algebra. So this is where you have an integral, like this one, the integral of 1 over the square root of 1 over 1 minus the square root of x, where you have a very obvious u and not a very obvious du, but we can get one on top by using algebra. And the way we do this typically is one of two methods. We either cleverly write an expression for 1, or we cleverly write an expression for 0. And what it does is if du is related to u, it may very easily help us to get a du on top. So let's look at this example. We want to do this integral. We have a square root of x. We'd like to say this is u, but there's no du. We multiply through by square root of x over square root of x, which is, just 1, of course. And now, because the derivative of the root of x is 1 over 2 square root of x, we now have, up to a constant, our du. So we multiply by the negative 2 to get the constant to work out perfectly. And now we have a 1 minus u, because I said this whole thing is u. So we have 1 minus u over u du. And of course, we can integrate that pretty straightforwardly. The second case is this one, e to the x minus 1 in the denominator. So this is another case where it is helpful, but this time we're going to actually rewrite 0 instead of 1. So e to the x minus e to the x, that's 0, of course. And the reason I did this negative multiplication through here is so I can get the denominator and the numerator to be equal by using this method. So I got e to the x minus 1 up here, and I got it down here. So that's just 1. And what's left over is this minus e to the x, so that's this term. And this term, of course, is just x. In this term, we have a u, this is our u, and this is our du, because the derivative at the bottom is just e to the x, right? So now we just have negative x minus the natural log of e to the x minus 1 by u-substitution. So next technique, integration by parts. So you may be familiar with the product rule. It says that the derivative of u times v, two functions of x with respect to x, is u prime v plus v prime u. And all that integration by parts says is if you integrate both sides, this, the integral, the derivative cancel. You get uv, and then you integrate this, and you get v du plus u dv, where the du or the dv, they just stand for like the v prime and the u prime respectively. Accordingly, I should say. Then you rearrange the terms like this, subtract from both sides, and then you get integral of u dv is uv minus the integral of v du. This is the typical way people write this expression. But what this really means is if you have a function u and a function dv that are multiplied by each other in an integral, you can just integrate one of the functions, which is a dv, and then do this term. If the integral is definite, you apply the boundary terms here, the upper and lower limits, and then differentiate this term. It comes in here, and then you can just integrate that. And this is super useful when this integral is much easier than this integral. So let's see some cases where that's the case. So the integral of ln of x, how do you even do that, right? Well, the answer is first of all, you might even say there's not even anything to integrate, but actually there is, because this dx is just a 1, right? You can put a 1 in here if you want. And it turns out that if you integrate 1, you get x. Shocker, right? X ln of x is the boundary term from integrating the 1. And then ln of x, you differentiate that, and you get, x from this integration, and then 1 over x from the differentiation. And that's just 1. Integral of 1 is just x. So this is our full integral. See how easy that was? You have no idea how to integrate ln of x, and now you can do it. Similar example, arctan of x dx. You might have seen this, what's going to happen here. The same thing happens with the boundary term. We integrate, 1 again, and then we have x over 1 plus x squared, which is an ln of u. This is our u, and this is our du. So now it's 1/2 ln of 1 plus x squared. So those are pretty straightforward and similar examples. Here's a different example, which is a little bit more complicated. So we want to integrate e to the x sine of x. And it's not really clear how this integral will be simpler. I mean, these cases, it was clear that the algebra would cause this derivative to cancel this integral, or rather, in this case, for it to be integrable. But in this case, it's not really clear because taking derivatives, integrals isn't going to really do anything to these terms. But actually, in this case, this is the whole point, is that does nothing. So we take the integral of e to the x sine of x. This is our v, e to the x that we're integrating, and sine of x we're differentiating. So we integrate e to the x, that's just e to the x, and sine of x stays. And now in our integral, we differentiate sine of x, that gives you cosine of x, negatives from this. So now we have this. What are we going to do with this? Well, actually what we do is we do one more step of this. So we have e to the x sine x minus cos x from the next integration by parts of this integral here. It's negative because, this is positive. Now there's a negative from the overall. And then in this term, we have multiple negatives. We have this negative. We have the new negative from this thing here. And then we have the other negative from derivative of cosine is negative sine. So the three negatives mean there's just one negative now. So minus e to the x sine of x. And this is equal to the integral of e to the x sine of x, as we said before. And you might notice if this thing is like some quantity, like suppose that this thing is q of x, right? Well, this thing is also q of x. So we can just, add this to this. We can just add this to both sides. Now we have two of these. We have 2q, if you like. So that tells us this thing here, e to the x sine x minus cos x, is 2q. So 1q, or the integral we're looking for, in other words, is just add this here, divide by 2, right? So hopefully the algebra is clear. I just said this is something. I'll put it over here. Now we have two of those somethings. We divide by 2, and that gives you this integral equals to this. The 1/2 is introduced here. So hopefully that's clear. Next technique, the tabular method for p integration by parts. You might have seen it was a little bit tedious keeping track of what was going on there. It can be even worse. Like something that you guys might have noticed is if you have like an x in here, so you want to integrate x sine of something, x sine x, x sine of x, we'll say. Then you can just take the derivative of this, and then you just have to integrate, you have to integrate cosine, negative cosine, but you get the point. So if you have a polynomial, you can just keep taking derivatives and kill it, and then this integral will be super easy to do. Like notwithstanding these like weird cancellations we did here. But if you have a higher order polynomial, you might need to do it multiple times. Like if there's 4x, if you have x to the fourth, you need to take 4 derivatives to kill it. So this is where we get the tabular method from. So we write down the derivatives of u and v up to the needed for multiple integration by parts, and the signs will alternate because, there's a negative in the integral of v du, and that negative will carry over into the next integration by parts. It'll be 2 negatives, so it'll be positive. So here's the example. So we want to integrate x fourth cos x dx. So the thing we're differentiating is x to the fourth. The thing we're integrating is cos of x. So the first thing we do is we differentiate. We get x fourth sine x minus 4x cubed sine x dx. We have to do this like 3 more times. So just put it in a table. So differentiate the terms, keep differentiating, just like this. Go down the table. X fourth, 4x cubed, 12x squared, 24x, 24. Each term is a derivative of the term above it. And then we're integrating this term, sine x minus cos x minus sine cos, and then sine. And hopefully that's straightforward. And then you can see that the only things that will say, oh yeah, the signs are alternating, of course. It starts off positive because this term's positive. So what you'll see is that the actual total thing is just you add up this term times this term times the sign, plus this term times the sign, this and so on and so forth. And then you get our final integral. So this table lets you just keep taking the derivatives and not have to really worry about what's going on. It makes it much more compact to write. So there you have it. Now, next method is trig sub and trig integrals. They're related, even though they're 2 different methods. So basically, the idea of trig sub and trig integrals is to use an identity, a trig identity, to simplify an integral. So sometimes we'll need to draw triangles. I'll show you why in a second, but let's just do one of the integrals first. We're going to integrate cosine squared of x dx. So the key here is we use this identity. Cosine of u plus v is cos u cos v minus sine u sine v. Cos squared of x is cos x, so just have u equals to v. So that tells us cosine of u plus 2, that's cosine of 2u, is equal to cosine squared x minus sine squared x. So we bring this over. Cos squared of x is cos of 2x plus sine squared x. And what we can do here is we can just say, we can do the same thing we did from before. We can say sine squared is 1 minus cosine squared, right? And then we bring the cosine squared over here like we did in the previous integral with e to the x sine of x, and we divide by 2. So now we have this integral is equal to cosine of 2x plus 1 over 2 integrated. And then we can just do this integral because it's straightforward. So that's the use of a trig identity. Now here's something you might not expect, is that trigonometric substitutions, trig identities can be used to evaluate an integral like this, which has no trig functions in it. And the reason it can is we do this technique. So you should use one of these identities. You should be looking for sine x plus sine squared plus cos squared equals 1, or 1 plus tan squared equals secant squared. And you see really clearly right here, 1 minus x squared. So 1 minus one of these guys squared is the other squared. That's the thing you're looking for. As soon as you see 1 minus something squared, or you see 1 plus something squared, you know exactly what you're doing. Or you see something squared minus 1, that tells you you're using the second one as well. So as soon as we see the 1 minus x squared, we know x equals cos u. This substitution will work for us. So we plug in this substitution, x equals cos u. Then dx, of course, is minus sine of u du, right? So minus sine of u du, x is cosine u, so you're going to have 1 minus cos squared is sine squared. Square root is just sine. So sine u on the bottom, and then minus sine u on top are going to cancel just to give an overall negative. And of course, x squared now is cosine squared of u. And we've just done this integral, so we know what it is. We know the integral is this. But there's a problem here, is that we have our integral in terms of u, and okay, u is arc cosine of x, right? Which is fine. But what about this sine of 2u term? How are we going to evaluate that, right? And the answer I'll show you just very quickly. That's what I mean by drawing triangles. So sine of u, it's important to notice, is 2 sine of u cosine u. So the cosine u term is just x, right? We need to find out what is sine of u. And the way we do that is simple. We know cosine of u is x, right? So here is u. Cosine is x, which can also be written, of course, as x over 1. So I'm basically drawing a right triangle. I'm saying in this right triangle, cosine of this angle, which I'm saying is u, is x. And this follows from the substitution that we've made. If that's the case, we use Pythagorean theorem. This side is the square root of 1 minus x squared. Because Pythagorean theorem, right? So now that we've done that, we know that sine of u is going to be square root of 1 minus x squared over 1, or square root of 1 minus x squared. So cosine of u times sine of u, factor of 2, comes out to x square root of 1 minus x squared. And therefore, this is our integral. Next technique, partial fractions. So this is useful for integrating rational functions you know how to factor, but it's kind of a pain. So this is just a fancy way of me saying this is where you factor the denominator into monomials. You can do it for binomials, linear binomials. You can do this with higher powers or like trinomials as well, but it's a little bit elaborate, so I don't want to go into it. So here's the example. You have this rational function. P of x is x minus 1. Q of x is x squared minus 5x plus 6. So we factor this. This is x minus 3, x minus 2, right? Just by inspection. And what the partial fractions theorem, if you want to call it that, says is that you can always write this as a over one factor plus b over another factor, where these two factors are constants regardless of anything else. As long as this numerator, I believe, has to be of a degree less than or equal to the degree of the denominator. So the question is, how do you find a and b? And the way you do it is by cross multiplying by x minus 3, x minus 2. And then you plug in the roots. Let me show you what I mean. So we have this expression, x minus 1 over this equals to a over this plus b over this. So we multiply everything through by this product. And then what we get is x minus 1, because these things canceled, equals a x minus 2, because x minus 3 canceled, plus b x minus 3. Now, it's super easy to find out what a and b are. This is true for all x, because the theorem says so. We plug in x equals 2. So then we just get negative b equals to 1. so b is minus 1. You plug in x equals to 3, you'll get 2 equals to a. So a is 2, b is minus 1. Super easy. And now we know that this is 2 over x minus 3 plus 1 over x minus 2. Just integrate those, they're logs. So now it's 2 ln of x minus 3 minus 2 ln of x minus 2. Partial fractions, super easy. Next thing we're going to do is an application of partial fractions called a tan x over 2 sub. So this can integrate any rational sine or cosine function. A substitution you make is u equals tan of x over 2, which is a super non-obvious substitution, but it's useful because sine of x here is 2u over 1 plus u squared du. Cos x is 1 minus u squared over, shouldn't be a du here. 1 minus u squared over 1 plus u squared, and dx is 2 over 1 plus u squared du. And you can derive these yourself if you like. It takes quite a lot of algebra, so I'm not going to go through it, but you can. And the point is this integrates any rational function of sine and cosine at all. And the reason why is because you're going to have these 1 plus u squared denominators, and they're going to cancel out super nicely. Let me give you an example of that. So here's the example, dx over 3 plus 4 cosine of x. How do you integrate this, right? No du in sight. But you do this u substitution. Dx is 2 over 1 plus u squared. In this denominator, you have 3, and you have 4, 1 minus u squared over 1 plus u squared. And now, this comes down and multiplies the denominator, because, it's a fraction. And then this multiplication will cancel out this term. And then you'll have 3, 1 plus u squared, plus 4, 1 minus u squared. So you have 7 minus u squared. And we can integrate that because partial fractions, right? We just said we can factor this, u minus square root of 7, u plus square root of 7, bring out a negative first. And then this is partial fractions. You solve for a and b, and this is what you get. And I promise this works for everything. Just do the substitution, memorize these replacements, and you'll be able to integrate any rational sine or cosine. Next one is geometry/symmetry. This is where you just solve the integral by looking at it and realizing what it is. Like, okay, this one's super obvious. Sine of x, odd function, even integral. So plot out sine of x, right? Sine of x looks like this. So you can see any area covered on the right side is covered negatively on the left side. So as long as the bounds of integration are symmetric about the y-axis, then the integral will be 0, because these will exactly cancel out. And that's what's happening here. Next one, the integral from 0 to 2 of square root of 4 minus x squared dx. Well, the square root of 4 minus x squared, you may be familiar with the expression x squared plus y squared equals to 4. This is the equation of a circle of radius 2 centered at the origin, right? And you can see that this is just the integral. You can rewrite this thing here. This is just the integral of y, right? But if we draw the circle, so here's the origin, here's a circle. Let's say the radius is 2. I'm not going to label it. You're just integrating y, and this is only the positive half of the circle because it's positive square root. You're just integrating y dx from 0 to 2. That's just the area of this quarter circle. So area of a circle of radius 2, that's pi r squared, 4 pi. And this is a quarter of the circle, so the area is just pi. Super easy, right? Otherwise, you could have done this integral using a trig substitution with x equals to 2 sine or cosine of theta. But this is much easier. Now here is a less obvious case of symmetry. I guess I shouldn't call this necessarily symmetry, but it is sort of symmetry. So we want to integrate 0 to 2 pi sine of x minus sine of x dx. So for clarity, I've just labeled this x minus sine of x as f of x. So the thing you can observe here is that x and sine of x have an interesting relationship. So the key here is that sine of 2 pi minus x is equal to negative sine of x. So f of 2 pi minus x is 2 pi minus f of x. And what do I mean by that? I'm saying x minus sine of x plug in 2 pi minus x for x in both of these cases, sine of x will become negative sine of x. And this will become 2 pi minus x. So both the x and the sine got a negative on them, and then we added 2 pi. So that's what this is saying here. I added 2 pi, and I put a negative on the original expression. That's what this is saying here. So f of 2 pi minus x is 2 pi minus f of x. And you'll notice that if we plug this again into sine of this is going to be the negative sine of x minus sine of x, because of the same rule as before, right? Sine of 2 pi minus x is minus sine of x. So sine of 2 pi minus f of x is minus sine of f of x, right? So at a point 2 pi minus x, the value of this function is the negative, this function is the negative of what the value was at a point x. So again, they exactly cancel out. Let me give it to you graphically. Here is the point x equals a small number. Here's the point 2 pi. And here's the point x minus that small number. This function is here. This function is here. So you integrate it, this integral will be 0, but this is true for all x. So that's the case of where symmetry can be used to evaluate this integral, where it's not as obvious as something like this. Next one, Feynman's trick. This one's often talked about. Differentiation under an integral sign with a me parameter. It's very useful for definite integrals, I should say. But it can also be used for indefinite. So let's start with that. I want to integrate x squared times e to the x dx, and for whatever reason, I don't want to do it by parts. So the key idea here is you integrate a function of a different variable, which generates this integral here, which generates the integrand, I mean. So the function is e to the ax. So a is just some dummy parameter. If you take two derivatives of this function, you'll drop down two factors of x. So you get x squared e to the ax. Now you let a equals to 1, you have this integral here. So we integrate this. The point here is that we can differentiate the derivative and the integral because they're over different integration variables. I won't prove it, but you can. So you integrate e to the ax, you get e to the ax over a. Take two derivatives of that, you're going to get e to the x over a, x squared minus 2x over a plus 2 over a squared. And then you evaluate that at a equals 1. And then you know that this integral is e to the x squared minus 2x plus 2. So in this case, kind of painless, maybe a little bit more work than we would have liked. But here's a case where it's actually much more useful because you couldn't integrate by parts. We want to do this integral. We want to do the integral of from 0 to 1 of x squared minus 1 over ln of x. No du in sight. Really not that much we can really do here. What you could do is you can try and say, oh, let me introduce a factor of x over x, right? So I have a derivative of ln of x, so I can integrate this. Then you're going to get something that looks like a u on the bottom. You're going to have e to the u, e to the something 3u. And then you're going to have what's called okay, I'm not sure what it's called. It's one of those classes of integrals that is not doable in terms of analytic functions. So you can't just like straight up integrate this. You have to use some kind of clever method. And the method we've used is Feynman's trick. And what we do is something we often do with Feynman's trick is we generalize the integral. So in this case, this is x squared. But what if it wasn't squared? What if we just generalize this to be x to the b? So that's what I've done here. This is just the case where b equals to 2. So you have this integral here. And this is the integral of x to the b minus 1 over ln of x. And the key point here is that this is e to the b ln of x, right? So now we have the e to the u over u, like we said before, but we can do something with it. We can, because this b is now a parameter, right? Like this dummy variable a from before. Notice that if you take a derivative of this, you will just cancel out the ln of x's, and that's exactly what we do. The derivative of I of b, this integral, with respect to b, it's the key point, is just x to the b. Because the ln of x cancels, the 1 goes away because of the derivative with respect to b, and then e to the b ln of x is just x to the b. We know how to integrate this because it's a definite integral, x to the b plus 1 over b plus 1. That's just going to be 1 over b plus 1. This is I prime of b, di db. So I of b is just ln of b plus 1 plus a constant. Then we know that if this b is 0, you have 1 minus 1, 0, integral of 0 is 0. So I of 0 is 0. That tells us c is 0. We solved for c, our integration constant. And that tells us that I is ln of b plus 1, so I of 2 is ln of 3. So this integral here is just natural log of 3. Wasn't that useful? So this idea of creating a dummy function and using the fundamental theorem of calculus with its integration constant is actually extremely useful. Here's another example. We're going to do this integral, and this is mainly only useful for definite integrals. The integral from minus infinity to infinity of sine of x over x dx. And what we do here is we take advantage of the similar type of generating function that will drop down a factor that will cancel our denominator. So in this case, we use e to the minus tx, and this is at t equals 0. If we wanted to make this 0, so it's just a 1, so it comes into this. So this is f of 0. T equals 0, we want to evaluate. So again, we take the derivative of the integral with respect to t, and we get this thing to cancel out, and then we have to do this integral here. But we can do this integral. We do it by parts. We've done this same integral, except that t was equal to 1, or minus 1, when we did the integration by parts. So you do it, you get negative 1 over 1 plus t squared, straightforwardly. Then you integrate this to find f of t, you get arctan of t plus c. We know that f of t equals infinity is 0. And how do we know that? We know that because t goes to infinity, this is just 0. This will overwhelm the whole integral. I don't care what this is. Oh, I should have pointed out, we use the evenness of this function to double the integral here. Not super important, but it's worth mentioning, because this is what kind of lets us say that the integral of e to the negative tx will go to 0, right? Because if we were integrating over negative numbers, then for t goes to infinity, this could be a positive number. This could actually blow up. So we couldn't say that f of infinity is 0 in that case. So hopefully that's clear. F of infinity is 0. So that tells us that c is pi over 2, because arctan of infinity is pi over 2. So f of 0 is pi over 2. That tells us that f this integral is pi, because it's twice the of pi over 2, so it's pi. And f of 0 is pi over 2, because arctan of 0 is 0. So next example, this is what's called the Gaussian integral over the whole real line of e to the minus x squared dx. So we again use the property of evenness to double the integral. We're going to call this integral I. And then we're going to do a very non-obvious generating function here. This generating function is e to the negative t squared, 1 plus x squared over 1 plus x squared. Jesus, where did that come from, right? But you can do it, and I'm only really using this. This is such a random function because I'm only doing this because it's a very straightforward way to evaluate this very difficult integral. So take my word for it, the substitution works, and we'll work through it. We'll call this f of t. Again, we take f prime of t, brings down a factor of negative 2t e to the minus t squared, because, product rule. The 1 plus x squared will come down, cancel this, and there you have it. So you have the integral of e to the negative t squared x squared from 0 to infinity dx. Because we factored out this e to the negative t squared, the 1 term. The 1 plus x squared came down and canceled the denominator, and the 2t came from the chain rule with the negative t squared, negative as well. So this is f prime of t. Can we integrate this? No, but we can do a u-substitution. We can say u equals to tx, right? And then du, of course, is t dx. So we borrow this t, put the dx, and now we have negative 2 e to the negative t squared integral e to the negative u squared du. So the key point here is that this integral, this Gaussian integral, is this thing here, the same value, right? So maybe it's a little bit confusing. I want to say this whole integral is, so this whole integral, what I really mean is it's equal to this, of course. Hopefully that's not confusing. So this thing here is equal to this. So we'll call this thing I. Negative 2 e to the negative t squared I is f prime of t is the point. And I is just a constant. So we don't have to worry about it being a function of t or anything. It's just the value of an integral. So we know f of 0 is pi over 2. And how do we know that? We know that because we know that because arctan again, I think. So yeah, so f of infinity is 0. Why is that? F of infinity is 0 because, let's see, this is f of t goes to infinity. So as t goes to infinity, this is just going to die off completely, right? So this integral will be 0. F of 0 is pi over 2 because f of 0 is just integral of 1 over 1 plus x squared. So that's arctan of x, so that's pi over 2. And the same arctan argument as before. So, actually, you can just do this integral. You can see that it's arctan like this. And then you just evaluate 0 infinity, and you'll see that same bounds apply. So the integral of, I'm just kind of writing it out in this case, the integral of f prime of t is going to be f of infinity minus f of 0. That's minus pi over 2. And that's minus 2I integral of e to the negative t squared dt. So that is just I squared, right? This is another factor of I. So I squared is negative pi over 2 over minus 2. So that's pi over 4. So I is square root of pi over 2. And then you double it because I kind of wrote I in a bad way. So the point is this integral here is equal to the root of pi. And we can evaluate this integral using this method. Now the next thing we're going to cover, probably the last one, is induction. This is an advanced technique where we use the value of one integral to find another integral's value. You need a base case and a recursion formula, and we're usually going to do it by parts. Let me show you what I mean. So suppose you want to integrate, you could say x cubed dx, you could say x to the 10th dx, I don't care. But we're going to just solve the general case where something is n, right? So this is a generalized case already. So we do this integral, we say, let's try it by parts, right? You could do it, like n times by parts. The key point is that we don't have to. So you do it once by parts, right? You get this straightforwardly. And the point here is that this term is just 0. Why? Because, when x is 0, then x to the n is 0, so this term is 0. When this is infinity, x to the n e to the negative x is 0 for all x because e to the negative x will dominate it. So all that tells us is this integral is equal to n times the n minus 1 thing. So if I call this integral f of n, because of n here, we know that f of n is nf of n minus 1, because it says so right here, right? And this may remind you of something. It's called the factorial. You just have to be sure that f of 0 is 1 to make sure that it lines up with a factorial. This is our so-called base case. So, we plug in at n equals 0. What's the integral from 0 to infinity of e to the negative x? Well, that's straightforward. It actually is just 1. So f of 0 is 1, and f of every subsequent thing is n times the lower thing. So this matches up perfectly with the definition of the factorial. See what we've done? This is called induction. So since we knew how to build kind of a ladder, we start with, okay, so here's n, and here's f, right? So n is 0, f is 1, n is 1, f is 1 times 1, because that's nf of n minus 1, so that's 1, n is 2, so now this is 2 times this, which is 2, and then n is 3, so now we have 3 times previous number, that's 6, and you'll notice this is following the factorial pattern. So this definition is equivalent. It will always be a factorial. The second case we're going to look at is the Gaussian integrals, which are a little bit more general, with an xn in front of them. So we do this integration by parts, right? Oh, and I want to point out, this is, of course, only when n is an even number, because if n is odd, they're all integers, of course. If n is an odd integer, this is an odd function, even interval, integral 0, right? So n is an even number, we do the integral by parts. We integrate x to the n, of course. So now we get this. And the reason we get this second x to the n plus 2 is the derivative of x squared will come down because of chain rule. That's where we get this 2 xn plus 2. One of them came from integrating x to the n. One of them came from this chain rule. So this boundary term here is going to be 0 from the same argument we made before. Or more accurately, this is going to be 0 because just the e to the negative x squared term will dominate at both of these points, so it's just 0. Therefore, we see that 2n, so this is just, okay, so let me cross this out. This is f of n plus 2. Just the integral itself, not the constant in front. So 2 over n plus 1, f of n plus 2, because n plus 2, right, is equal to f of n. And we know f of 0 is the square root of pi because we just did this integral for the case where there was no x to the n in front of it. So we know it's square root of pi. So what's happening here? Every time we go up by 2, we have to multiply by the okay, so if I move this over here, you'll have n plus 1 in the numerator, 2 in the denominator. Every time you increase n by 2, you have to divide by 2, you have to multiply by the odd number in between n and n plus 2. So really, you're just going to be multiplying all the odd numbers, starting from 1, all the way up to this smaller one, right? So you're multiplying every single odd number from n, from 1 to n plus 1. And how do we express that? Well, we have the square root of pi here. That's fine. And we have, so the way we write them as odd numbers is we write 2k plus 1 for some, natural numbers, right? And so, of course, we have to have the index, subtract 1, so that this will, in fact, be all the right odd numbers. So what's going on here is this is going to be the product of all these odd numbers. And the way we can write this is by using this factorial definition. So suppose you have 10 factorial, right? That's 10 times 9 times 8 times 7, and so on and so forth. And can we use this to just get the odd numbers out? And the answer is we can't, because we just have to divide out all the even number terms, and we'll have our answer, right? So how do we get the even number terms? We need to divide out, okay, so the point is 10, 8, so on and so forth. This is 5 times 4 times 3 times 2 times 1, and each term multiplied by 2 will give you 10, 8, so on. So 5, 4, 3, 2, 1. Multiply each of these terms by 2, and you'll get all the even numbers you need to divide out of this term. So, but what is this? This is just a factorial again, right? Because you need to be multiplying them together. So n factorial is on top, that's the whole thing. N over 2 factorial is on the bottom to divide these out. And for each term in here, you need to introduce a factor of 2 to the of 2, right? So it should be 2 to the n over 2 because we only have n over 2 terms in this factorial. But there's another factor of 2 to the n over 2 that comes from this division over here. So overall, we have 2 to the n times n over 2 factorial on the bottom and n factorial on the top will give us the product of all the odd numbers. Multiply that by square root of pi, and that's actually the closed form solution for this integral. And it's super cool that there is a closed form solution. How would you ever get something like this with these factorials, right? You just kind of have to work through it, but we can do it. And the last thing I want to talk about is complex analysis. This is a really useful technique, but it's very advanced, so I won't blame you for skipping over it. So here's what's going on. We want to do a complicated integral, and oftentimes it's useful to do it using imaginary numbers. So what's going on here is you have a circle, right, of radius 1, the unit circle, and this is kind of like polar coordinates if you've seen those before. This x coordinates cosine theta, this is sine theta, but they say here, cosine theta plus I sine theta is really this point. That's what e to the I theta is saying. Any point on this circle can be expressed as e to the I theta, because we write e to the I theta as cos theta plus I sine theta. You can kind of think of this as saying that a point xy is r cos theta, cos, and then r sine of theta, because the real and imaginary parts are kind of like components of a vector, in the sense that in the drawing here, imaginary real numbers, they're kind of orthogonal. See? So it's kind of like you're writing them as different unit vectors. So any point on this circle can be written in this way as r e to the I theta. In this case, r is 1 because it's on the unit circle. And then we call that z. Using this property, e to the ix is cos x plus I sine of x, you should know. And this gives us a useful trig identity that we can see. Sine of x is e to the ix minus e to the minus ix over 2i. You can prove that pretty easily using sine of negative x is equal to negative sine of x. You can verify this. That's also sine h of ix times minus I. And then equivalently for cosine, you have this formula. So the way we use these methods to evaluate integrals is using what are called complex contour integrals. That I have a video linked in the description that will explain to you what those are. So I want to give you some background before you watch it. They are very useful for evaluating infinite definite integrals. So here's some terminology you have to talk about. A pole. A pole is when a function we're integrating blows up. So 1 over z minus 3 is a pole at z equals to 3, because this goes to infinity. But this function, e to the 1 over z minus 1, has a pole at z equals to 1, because this thing will blow up to infinity, and that will blow this up to infinity. So the residue. Residue is just this definition here. The residue of a function at a point is equal to the limit as z goes to that point of this expression here, where n is the lowest number greater than or equal to 1, such a limit exists and is finite. Example, residue of 1 over z minus 3 at z equals to 3 is 1, because limit z tends to 3 of, okay, so let's try it. So we start with n equals 1, because it's the lowest, we try it, trial and error. So z minus 3 to the 1, f of z, that's just 1. So derivative at minus 1, derivative is 0, that's just nothing. 0 factorial, that's nothing, it's just 1, so it's just 1. So for most of the poles we're going to deal with, the residue has to be evaluated at a pole. Most of the residues at the poles we're looking at are going to just be simple like this. And that's the end of the presentation. I have a presentation on contour integrals linked in the description. I hope you guys found that informative.